Welcome everyone to the second episode of this short video series called The Mathematics of Music. Last time we saw how sound occurs when molecules of air collide with each other because of an oscillation, like the speaker's membrane moving back and forth. But the membrane wasn't oscillating randomly. That oscillation can either be swift or slow, and the measure of that speed is what we call frequency. Most instruments today are tuned with a pitchfork set to a frequency of 440 Hz, which represents the note A. The historical reason behind that specific frequency is not relevant to the purpose of this video, but I linked information in the description if you're curious. That being said, to find all other notes besides A, we need to use mathematical ratios. The legend goes that Pythagoras of Samos, the notorious Greek mathematician, discovered the nature of musical tuning by listening to blacksmiths striking iron hammerheads on anvils. He found that some hammers sounded pleasant when struck together and others not. The Greek polymath then weighted hammers that sounded pleasant together and found the ratios between the weights. By far, the most pleasing sound occurs when there is a ratio of 2:1. For instance, two hammers of respectively 12 pounds and 6 pounds striking an anvil at the same time will make it appear as if there is only one sound. That is what we call an octave. Now remember, I previously said that all instruments are tuned to the specific frequency of A equals 440 Hz. Therefore, if we want to add an octave to that note, we need to make it vibrate twice as fast. Thus, the most pleasing sound we can add will have a frequency of 880 Hz. Pythagoras then discovered several other ratios that sounded quite enjoyable. 3:2, which sounds like this, 4:3, which sounds like this, and as a reference, this is what more complicated ratios sound like. 45 against 32 sounds like this, and 16 against 15 sounds like this. Thereupon, Pythagoras started experimenting with simple ratios and then developed what we call today the Pythagorean tuning system. This is a system that stacks 3:2 ratios on top of each other, like this picture demonstrates. The problem is that the more we stack ratios of 3:2 on top of each other, the more complex the ratios become, which doesn't sound very pleasing to the ear. Pythagoras found the importance of ratios in music, but it required little less than 2 millennia before there was any documentation on another essential aspect of music theory, the harmonic series. Here is a quick demonstration of the harmonic series. I will use an audio software called Ableton Live. In this audio file, you can hear me sing at a frequency of 220 Hz, meaning my vocal cords vacillate around 220 times per second. Let's isolate parts of that audio file. The biggest spike in intensity we see is at 220 Hz. We hear the noise, but muffled. This is called the first harmonic. Then the second highest peak is at 440 Hz. This is the second harmonic. Afterwards we have 660 Hz. The third harmonic. All other harmonics decrease in intensity thereafter. These variations in harmonic intensity is how a piano and a guitar can produce the same pitch with similar frequencies but have a different timbre. By that I mean our ears can distinguish a piano from a guitar playing even if they're playing the same note. These variations are due to the fact that they're made of different materials, so the molecules don't vibrate the same way. To summarize, different intensities in harmonics create different timbres. In this small analysis I've given, we can notice that the ratio phenomenon that Pythagoras discovered finds application within our own voice. The second peak of intensity which we call the second harmonic, has a 2-to-1 ratio with the initial pitch. However, the following peaks actually respect a maths equation called, conveniently, the Harmonics series. If you take the number 1 and you add its half, then its third, then its fourth, and you do so until infinity, you will get what we call in mathematics an infinite series. It can be represented by this complex-looking formula, and mathematicians like to analyze series like this one. This equation has a direct application to timbre. When I produced the frequency of 220 Hz, it also added its third, its fourth, its fifth, and so on until theoretically infinity. So what we truly hear is not one singular frequency, but an infinity of frequencies that decrease with intensity the higher they get. Some people specialize in isolating specific harmonics within their own voice, like this excerpt. Depending on the shape of the mouth, the sound waves will bounce on different tissues, and the molecules that make up these tissues will vibrate differently. Thusly, we can have different sounds depending on different mouth shapes. I will demonstrate that idea on my guitar. These strings can vibrate from the bridge to the nut, which represents a length of around 61 centimeters for this particular guitar. If I take half of this length, we can get the first harmonic. And notice that this phenomenon can only be heard at this precise location. If I go to the third of the length, starting from either the nut or the bridge, you can hear the third harmonic. Perhaps you've noticed, but this is what the introduction to the sound Roundabout by Yes utilizes. To sum things up, Pythagoras discovered the ratios in music, and then we found that sound are very complex and are actually made of an infinite amount of frequencies that we call harmonics. Thank you all for listening. Hope you've learned something that you find interesting, and I hope to see you next time.